Thank you so much, Olga, for the wonderful introduction and also for all of your hard work to organize these symposia. I think it's really an excellent opportunity to get to talk with colleagues and share recent results. I've really been impressed impressed with and enjoyed the previous talks, and it's a hard act to follow. So I wanted to say thank you so much for the opportunity to present today. I also wanted to thank my group members who helped make this work possible, in particular, Abhi Ganis and Chaman Gupta. But before I move on, I want to make sure, can you see my cursor and does everything look okay? Awesome. So I also wanted to plug, if you are interested in the research we're doing, if you like what you see, please don't hesitate to reach out to me. We've got a couple postdoc positions open and graduate positions available if you're interested in moving to the beautiful Pacific Northwest. I also wanted to thank Anupam Pant, Matt Crane, and Bennett Smith. These are former group members who did some work and who have since moved on, but they were really instrumental in laying the foundation for the experiments that I'll present today. And then you also see in my talk pointers to many colleagues and close collaborators who have really helped us with many of these experiments and contributed a lot to help us answer some of the questions we've been pursuing. And then, of course, none of this work would have been possible without substantial support from multiple different agencies. The NSF, the Air Force, ONR, DOE have truly given us a wonderful foundation to build from and support all of our efforts. So I want to thank everybody, and especially you and the audience for coming today to attend the talk. I also wanted to mention, I hope someday to give you a tour of the lab in person once the COVID situation settles down. The spring MRS meeting was supposed to be in Seattle this coming spring quarter, but unfortunately, my guess is that that's not going to happen, at least for another year. I think another meeting is scheduled. I think in 22, it's scheduled, I think, for Hawaii. And then I think in 23, it's back in Seattle. So hopefully, if you are able to make it for the spring MRS in the 2023 spring quarter, I'd love to give you a tour of the lab. You can land at SeaTac and take a light rail past the Space Needle to campus. So it's not too tough to get around in Seattle, not as hard as it used to be. I'd like to give a quick overview of today's talk. I'm going to try to keep it to within 45 minutes and give a quick overview of how we're growing nanodiamonds and trying to control their doping with molecular precursors. And this has been a long-standing interest in my group, and we've had some progress recently with the silicon split vacancy defect, and more recently with nitrogen doping. And I'd like to share those results today, sort of how we make these materials in terms of high pressure, high temperature synthesis. And also talk about some simulations. We've done some collaborations with Xiaosong Li's group in the chemistry department at UW to study the pressure dependence of the optical photoluminescence of the silicon split vacancy in nanodiamonds. And then finally, I'll finish with a vignette of a couple future directions, ongoing efforts that we haven't published yet. We're just either having this work in review or submission. So with that, without further ado, I'd like to jump into the intro. I don't think I have to explain to this audience why you should be excited about nanodiamonds. After the previous speakers' introductions and multiple recent international conferences, there's a lot of interest in using nanodiamonds for quantum sensing applications, using optically detected magnetic resonance with nanometer scale volumes. It's really amazing what's possible trying to sense molecular species with single spins in an NB center. There's a lot of excellent work going on in biolabeling with nanodiamond. Point defects in diamond have unique stability properties. They don't photobleach, they don't blink, and you can label cells for long periods or other structures to get information about where certain components are within a cell, what the temperatures are, and potentially sensing molecular species. We've seen at least one talk earlier this series with really beautiful results using ODMR to sense chemical radicals that are produced in a cell. There's also a lot of exciting work with diamond going on in photocatalysis. This is a paper from Nature Materials about 7 years ago using the photoelectrons in diamond to fix N2 to ammonia. This is a really energy intensive process. The Haber-Bosch process consumes about 3% of global energy budgets. And there's some very exciting work going on in the Hammers lab at the University of Wisconsin using diamonds to do photocatalysis. And also in basic research, there's a lot of interest in using diamonds. They're studying diamonds from meteoric materials to understand the evolution of the solar system, the history of solar structure. So nanodiamonds are truly ubiquitous. They span from geological context to biology to astrophysics. And it's a really exciting field to be in. And as we've seen earlier from previous talks, there are a lot of exciting applications in both applied science and basic science. So my group's research is really focused on trying to develop novel molecular methods to control point defects in diamond. Historically, nanodiamonds were first discovered looking at the products of high explosives that are detonated in a chamber. Recovering that soot, you can process the soot and recover very impressive quantities of diamonds. They have industrial scalability, and you can make large amounts of nanodiamond with this approach. One challenge, though, in detonation synthesis is that you often also recover some amorphous soot materials or metallic species on the surface of the diamonds, and a lot of work has to go into refining these materials so that you could use them in, for instance, chemical vapor deposition, diamond thin film growth. And during my postdoc, I started to begin to focus on some high pressure methods to convert amorphous carbon materials to diamond. And we uncovered some accidental doping of these materials with nitrogen and silicon atoms, but we really couldn't control or fully explain why these atoms were there and how to put them where we want them to be. So more recently, my group's been focusing on more controlled molecular synthetic methods to try to improve the monodispersity, but more so the point defect microstructure within nanodiamonds, trying to develop methods where you could call your shot and develop any type of well-known point defect that exists thermodynamically, but potentially develop new point defects that have never been made before using molecular precursors. This is an ongoing challenge, and there are many groups. Fellhammer's lab and Fedor Yelezko's group have started to do some very nice work with high pressure doping as well. So many groups that I'll refer to later on in the talk have developed methods using multi-anvil press techniques and things. And this is a really exciting time to be working and making nanodiamond, because there are a lot of great ideas to how to control the point defect microstructure in these materials. So just to talk in a little bit more depth about these challenges, this is an illustration of the detonation process. And I wanted to point to a review article that Olga recently published. It's a really great review on diamond synthesis and characterization. There are really great sections on a variety of different methods, including the detonation growth. And in this process, you have very rapid, high pressure, high temperature shock waves that can convert amorphous carbon to diamond materials. This is what the detonation diamonds look like when received, often when they're recovered from the detonation chamber. And you can get grams or kilograms of this material. But one challenge is you can see the color of these diamonds. It's sort of kind of charcoal in appearance, and air oxidation can remove some of those impurities. But there's some really nice work published a few years ago in Carbon using, I think this was mass spec or in ICP mass spectroscopy to look for atomic level, parts per million, parts per billion level elemental impurities. And there's really a surprising number of elements that you can find in these materials, largely from the detonation chamber. It could be the detonation chamber or the refining setups used to anneal these materials in air, post-process them. You can get a lot of transition metal impurities that can affect things like optically detected magnetic resonance. So more refined methods have been developed in recent years, particularly in chemical vapor deposition. You can grow extremely high quality, high purity diamond materials using these detonation diamonds as seeds using chemical vapor deposition. And element 6 has a wonderful variety of different CVD materials you can buy with extremely high purities and very little transition metal, nitrogen, you name it. Except in chemical vapor deposition, there's a challenge with hydrogen. Oftentimes you have a fair amount of hydrogen left over in the film, and the hydrogen atoms can passivate color centers in diamond like the NV center, which can reduce their brightness or the yield you get following implantation. Hydrogen is kind of a challenging mystery element that has to be considered when trying to make point defects in a CVD approach. There's another paper I wanted to refer to that was published back in 2012 in Nature Communications that claimed that you could grow nanodiamonds using ethanol in an argon plasma at atmospheric pressure. And we've tried to reproduce this paper, and it's been really challenging in our hands, at least. We've not been able to reproduce growing nanodiamonds with ethanol. We've been able to make metal nanocrystals. We think that we're growing copper nanocrystals from the plasma arc power supply that just volatilizes the metal. But this is CVD still remains a wonderful way of growing very high purity materials. You can grow thin films, you can mill these materials and get extremely high quality diamonds, or overgrow on detonation nanodiamonds. There's another approach frequently used in the literature of high pressure, high temperature synthesis. This is very famous. I don't think I have to introduce this or dwell on it much. I think everybody's seen this before. But in the multi-anvil press or toroid press, you can grow large amounts, milligrams of material, get to very high pressures, 15 GPa or so, very high temperatures, over 1,000 degrees Celsius routinely, very easily. But a challenge is controlling the kinetics of this process. These things are slow to heat up, slow to cool down. And also it's difficult to see inside of the chamber when you're doing synthesis. It's hard to know what you're growing in real time. So my group is focused on a complementary approach. This isn't going to solve all of the problems I've identified in particular, but we use a laser heated diamond anvil cell to grow our material. And if you've not seen one of these devices before, I think many of you have encountered these previously. But for those of you who may not have seen this technique before, effectively you take two gem quality diamonds. These are often polished in a 100 plane. There's a metal gasket typically made of rhenium, and they're very small cross sections. You have a very small area, and a modest force over this small area can generate tremendous pressures, tens of gigapascals routinely. And one advantage of the diamond anvil cell, you can get higher pressures. You can also have a window into the chamber. You can look through the diamonds and see what's happening inside. And this is a really great opportunity to do real-time in situ characterization of the materials that you're growing. So typically what we use is a laser to do both heating and also spectroscopy. I'll return to this momentarily in a few slides. We also use ruby crystals. These are chromium doped alumina grains, effectively just ruby shards, that we can look at the chromium crystal field splitting and measure the pressure in the diamond anvil cell. So we can measure the pressure from the ruby, and we use optical emission from the carbon aerogel while it's being laser heated, basically the Planck emission, the black body spectrum, to get the temperature. And I'll talk a little bit more about that in a few slides. Just to illustrate what's possible with pressure, this is a really neat technique. And for instance, you could start with a silicon material. Everybody who's worked with silicon has seen that it's a cubic crystal structure. You've got the same crystal lattice as diamond. And if you squeeze silicon to above 10 GPa, you can make a tetragonal phase. You can effectively compress the cube in one direction. But if you relax that pressure, surprisingly, you can recover a hexagonal phase of silicon. And this is a really amazing phase transition, because you go from a material that has an indirect band gap to a material that has a direct band gap. This is a very surprising electronic structure property change that you can reach with pressure. Just to illustrate some of the other neat things you can see with pressure. As you squeeze the crystal, you can see the Raman spectrum blue shift. You can see this, both the frequency of the cubic Raman spectrum change, and new phases arise with their own unique Raman spectra. So I'll refer to this later on a bit in the talk. So what I'd like to do next is talk a bit more about the synthesis methods we use in the diamond anvil cell. So in comparison with the detonation approach, we also start with small molecule precursors. Most high explosives that are detonated are some kind of nitrogen-rich hydrocarbon molecule that's very unstable, like trinitrotoluene. We're starting with resorcinol and formaldehyde. We use either a base catalyzed or an acid catalyzed cross-linking reaction in the solvent. It could be water. More recently, we've been working with acetonitrile. And we effectively make jello. This is a gel that forms due to sol-gel cross-linking. There are a number of electrophilic addition steps and condensation, polycondensation reactions where we produce some water in this reaction, but effectively we make some hydrocarbon gel that has a lot of hydrogen and a lot of oxygen from the precursor molecules. So to get rid of the hydrogen and oxygen, we pyrolyze the hydrocarbon aerogel at very high temperatures, typically above 1,000 Celsius. In an inert atmosphere, it could be argon or nitrogen, and we make an amorphous carbon aerogel. So these are amorphous carbon aerogels that have unique properties. They were originally developed for high surface area electrochemical supercapacitors, but they have some very high surface area and high porosity properties that make them very useful in growing nanodiamonds. So each of these little cartoon spheres you can think of as amorphous carbon. It's at least 99.99% carbon. There is hydrogen left over in the material. We can't get rid of all of it. We estimate it's on the order of maybe ppm level hydrogen from infrared absorption spectroscopy. But the idea is we can take this high surface area nanoscale amorphous carbon sphere and try to convert it into a nanodiamond structure within the diamond anvil cell. So the first step is we load the carbon aerogel into the diamond anvil cell. We use cryogenic liquid noble gases. This is either argon or neon so far, but we're very interested in moving on to working with xenon for reasons I'll discuss later. But we can effectively fill the pores of the aerogel with a liquid noble gas. We can then compress the noble gas and freeze it at atmospheric pressure at about 1.8 gigapascals. Argon will freeze into a face-centered cubic crystal structure that's chemically inert, or at least we thought it was completely chemically inert previously, and it's optically transparent. So once we form this filling, once we fill the amorphous carbon aerogel, we laser heat it with a really high intensity, high irradiance fiber laser. This is either a neodymium YAG laser or a ytterbium fiber laser through the windows. We can also focus Raman lasers to do spectroscopy of these materials in situ. And then one property of the aerogel I wanted to point out is that because of its composition of carbon and very high surface area, it has an extremely high optical absorption coefficient. The reflection coefficient is less in all directions over a very wide wavelength range. Is effectively zero. It's on the order of 1 or 2%. So it's almost like a black hole that every photon that hits it sticks and can't escape. It also has a really low thermal conductivity because of its sort of mass fractal microstructure. So it really doesn't conduct heat that well. So we can really heat this stuff up to very high temperatures. So here's a cartoon sort of schematic of the process. We've got the diamond anvil itself. We've got a ruby crystal, the amorphous carbon aerogel that we fill with chemically inert noble gas. We squeeze this system to an arbitrary pressure of interest, and then we use laser heating to heat the amorphous carbon and drive a phase transition to diamond from amorphous carbon. We can then follow up with a second laser and look for Raman spectra or photoluminescence within the diamond anvil cell itself. So this is a quick illustration of what things look like before and after laser heating. This is the amorphous carbon aerogel in the DAC at high pressure. And it basically has no unique features. It just looks like a black lump of coal. But after we laser heat it, you can start to see a very quick and rapid change in color. At least it becomes much more translucent and scatters a lot more light. And so this is the first bit of evidence that we have that we're seeing a phase change for this material. We can recover the material from the diamond anvil cell. This is amorphous carbon that's been pressurized but not laser heated, and do electron diffraction. It still looks very amorphous in its electron diffraction. If we laser heat the carbon aerogel at high pressure, we can recover that material and look at the electron diffraction. You see these very distinct diffraction rings. So these are electron diffraction patterns that index to cubic crystalline diamond. So this is the first evidence that we've been able to crystallographically convert the phase from amorphous carbon to diamond. I also wanted to share, we've done some X-ray absorption spectroscopy measurements. This is a really terrific user facility at the Advanced Light Source at UC Berkeley, Beamline 532. And we've looked at the amorphous carbon aerogel X-ray absorption spectrum. You can see really pronounced 1s to pi star transitions that indicate graphite or graphitic carbon at about 285 electron volts. The diamond material that we recover has a dip in its electronic density of states at about 302 electron volts that maps onto detonation nanodiamonds. This is a spectrum from detonation nanodiamonds. This is a spectrum of bulk diamond materials. So this is some additional evidence that we have a phase conversion from amorphous carbon to diamond. But interestingly, there's some pre-edge features that also index to a graphitic type of microstructure. And we weren't quite sure what would explain this type of surface reconstruction. So one of the first collaborative papers I published with Jiasong Li's group at UW was doing some ab initio quantum cluster calculations of nanodiamonds. And remember, in this experiment, there's nothing but argon around the diamond material to bond, really. So the surface atoms of the diamond most likely will bond with each other. There's really nothing else around to bond with. In this paper, we did some calculations of how many layers do you have to go from the surface into the core to really identify a diamond phase. And there are indeed several, at least monolayers of reconstructed surface atoms that are forming kind of a combination of sp2 and sp3 bonds. And we think this explains some of the pre-edge X-ray absorption spectra. We can also zoom in to look at the TM of this material, and you can see these characteristic lattice fringes. These are these index to 111 D spacings. I apologize that the scale bar somehow escaped this image. This is about a 2 nanometer grain. This is about a 4 nanometer grain. These are very small grain sizes that have this sort of reconstructed surface. But surprisingly, way back in 2011, when we first looked at the PL of these materials, we saw really pronounced emission at about 638 nanometers and about 740 nanometers. And I had never worked with diamond before and was scratching my head, wondering what is this emission coming from? We were just trying to get Raman and had all of this photoluminescence messing up our Raman signal. And looking into the literature, these peaks index very nicely to the negatively charged NV center and the negatively charged silicon split vacancy center. So we had been making these point defects accidentally. And more recently, my group's been focusing on how can we control these defects? Where are they coming from? And how can we get rid of them and then add them back with molecular control? So the first defect that we focused on is the silicon split vacancy. We really weren't sure why we were getting silicon when we hadn't added it to our reaction. But in our initial sol-gel reaction process, we had added all of our reagents within a silica beaker in basic conditions. And if you have a basic aqueous medium in glass, effectively you etch away the glass at least ppm levels. You can dope accidentally, inadvertently with etching your silica glassware. So we had an idea. Matt Crane led this effort, and effectively what we did is just switch to plastic glassware. It was a really simple fix. And instead of working in water, we started working in an organic solvent that was acidic instead of basic and had much faster gelation. And you can see in this comparative spectrum, the dash spectrum is what we had originally. And simply by switching to the plastic container, we completely got rid of the silicon split vacancy peak. It completely vanished. This peak here is from Ruby. This is the chromium doped aluminum oxide we use as a pressure sensor. So effectively this emission totally vanished. I have to apologize. This spectrum here is at high pressure. So the NV center is shifted from 640 to blue shifts at high pressure. But just to give a quick overview, we were able to get rid of this silicon in the PL. So we sent our sample to our collaborator, Rhonda Stroud at the Naval Research Lab and said, Rhonda, we think we've made diamond and we don't think there are any silicon atoms in this at all. Can you take a look in your TM and let us know what you see? And the first thing that she saw in the materials that we had made were silicon atoms. And we had no idea where these were coming from. They were clearly not doping the diamonds to create photoluminescence. And I apologize, I don't have a movie of this, but Rhonda was able to see these silicon atoms moving on the diamond materials. So we think these are just silicon atoms she was able to see from vacuum pump oil in the lab. We think these are silicon grease, effectively silicon atoms that are diffusing on the surface. So we were confident that these atoms were not embedded within the diamonds themselves. They were moving around on the surfaces of the diamond nanocrystals we had made. But the next step was, could we deliberately add the silicon back into the diamond nanocrystals? So the approach that we took was using a tetraethyl orthoxysilane molecular dopant. We added this in with resorcinol and formaldehyde, did the same type of gelation reaction in a plastic container. And then we looked at the X-ray fluorescence spectrum of the silicon doped material. And sure enough, we were able to see silicon atoms show up in this doped material, which we didn't see in the undoped controls. But more excitingly, when we went through this high pressure, high temperature laser heating process, we could see huge amounts of silicon split vacancy emission from this material. And in comparison with a control undoped sample, there's no silicon doping. No silicon split vacancy emission, and we can vary this concentration with exquisite precision using parts per trillion, parts per billion doping levels up to parts per thousand. In the limit, you could even make a silicon carbide material, which is an interesting future direction to consider in terms of quantum information science. But also one surprise I wanted to share is that beyond seeing just silicon atoms in this material, Rhonda was also able to see argon atoms. And this caught us completely by surprise. We had no idea that, we just assumed that argon would be chemically inert and not mix with the carbon material. We thought it would prevent bonding at the surfaces of the diamonds, but Rhonda was able to prove very convincingly from the carbon, or rather argon K alpha X-ray fluorescence spectrum, and also an argon 2,3 edge EELS spectrum in her neon TEM microscope at the Naval Research Lab, that we clearly had argon atoms embedded within our recovered diamond material. So this is a really surprising result that we published last year. And it sets the stage that you could imagine switching the pressure medium to xenon from argon and potentially doping the nanodiamonds with xenon would lead to some potentially very useful point defects for quantum information science applications, or maybe NMR applications as well. So we wanted to do a bit more characterization and understand, why are we getting argon? We're really scratching our heads. What's going on here? How can we get argon atoms within a diamond crystal starting from amorphous carbon? So this is a spectrum just to illustrate how we're measuring the temperature in this experiment. We shine a high intensity CW laser, ytterbium fiber laser, typically on the amorphous carbon. We get white hot Planck emission spectra, extremely bright Planck emission. And so we can disperse this emission onto a spectrometer, fit the UV invisible region to Planck's function, and extract a temperature that typically ranges between 1500 Kelvin and on the order of 2000 Kelvin. So we can reach temperatures, at least for brief time points, that are much higher than what can be reached in, say, a multi-anvil press. It's really challenging to reach these types of really high temperatures. And Matt Crane did a really terrific job looking at this very systematically as a function of the irradiance. And at certain irradiance thresholds, he noticed really sharp spikes in the temperature. He would see some baseline temperature around 1300 Kelvin, 1400 Kelvin. Then all of a sudden it would jump to 2000 Kelvin. And we really weren't quite sure what was going on. So we started to think more critically about this experiment, and zooming into the microstructure of the aerogel. You can think of these as tiny little spheres that are being heated by the laser, and they're surrounded by argon. And we got to thinking, maybe we could heat these spheres up hot enough that it would melt the solid argon crystal surrounding them, the pressure medium, and effectively convert that solid argon into a superfluid, not quite a gas. It's still very dense, but it would have a fluid-like superfluid character and have a much lower thermal conductivity. So the idea was we could potentially melt the solid crystal to make a supercritical argon insulator around the carbon material. If you compare we did our best to find the thermal conductivities of these materials. Fortunately for argon, there's a lot of great literature that's been measured, and the thermal conductivity of solid argon at around 20 gigapascals is just under a watt per meter Kelvin. And we can estimate from other molecular dynamic simulations that the thermal conductivity of supercritical, superfluid argon is about an order of magnitude less than that of the crystal. It just conducts heat less efficiently. So we did some numerical analytical calculations with these different thermal conductivities. And sure enough, if you plug in the superfluid conductivity, temperatures can jump to on the order of 2000 Kelvin. And if you start at with solid argon, these temperatures would be on the order of 1400, 1500 Kelvin. So you can easily explain this temperature jump in terms of just a change in the thermal conductivity of the surroundings of the aerogel. But and so our hypothesis is that this gaseous argon atoms are very mobile. They can diffuse very readily and potentially infiltrate the amorphous carbon before it crystallizes. And some of these argon atoms get trapped in the lattice, but we don't have a clear picture at the moment. Are these split vacancies? That we have some EDAX data or EDAX mapping that I'll share that clearly shows there might be some pockets of argon too, maybe bubbles of argon trapped in these materials, maybe at grain boundaries. So still an interesting question, but a really surprising sort of counterintuitive discovery that argon is not chemically inert. It dopes the diamonds. So I also wanted to share some really nice calculations that Xiaosong's group led in terms of studying the optical transitions of the silicon split vacancy as a function of pressure. This PhysRev-B paper is a great description of the different electronic mid-gap states of the negatively charged silicon split vacancy. So our group collaborated with Xiaosong effectively. We made high pressure measurements of the zero-phonon line ZPL of the split vacancy. And this is double blind. We didn't share our results with Xiaosong's lab. We just made the pressure-dependent ZPL measurements, and there's a shift of about 1 milli-electron volt per GPa, and this agrees very well with some other very nice measurements reported recently in the literature using multi-anvil materials grown in a multi-anvil press. And then we compared our results that were about 1 MeV per GPa with Xiaosong's calculations. They just used the lattice constant pressure dependence of diamond to make calculations of the ZPL pressure dependence. And their prediction was about 0.8 MeV per GPa, just about 1 MeV per GPa. So for a collaboration between theorists and experimentalists, this wasn't that bad, considering the assumptions we had to make. We had argon atoms throughout our lattice, and their surface reconstructions and a number of things that can shift the ZPL or internal strain effects. But Xiaosong's group did a great job just in terms of blind calculations. We're very pleased to see their agreement with our experiment. So with that summary, I'd like to wrap up my talk today with a few quick overviews of ongoing research, sort of building from these results in terms of molecular doping with silicon. More recently, a graduate student in my lab, Abby Gannis, has done a great job working with molecular precursors that are very rich in nitrogen. So the idea is we want to elevate the number of NV centers in our nanodiamonds, and what we haven't been able to get rid of the nitrogen like we were with silicon. There hasn't been a simple fix of just switching to a different type of glassware. We think they're fizzy-sorbed N2 molecules, possibly from the atmosphere, that dissociate at high temperature and pressure, that we just cannot get rid of. But we can at least try to add more nitrogen to the material and control the addition of nitrogen. So we started with this species, hexamethylene tetramine. This is an interesting molecule that looks a lot like a B center in diamond. If you replace 4 carbon atoms around a vacancy in a diamond, this is the definition of the B center. And we would like to control this at least concentration of nitrogen. And one hypothesis we were testing is, could we potentially dope this molecular precursor like hexamethylene tetramine and form B centers by preventing this molecule from dissociating enough, have 4 nitrogen atoms very close to each other at high pressure, high temperature conditions, and effectively convert to a B center. So the process is identical. We add this molecule to our acetonitrile solvent with resorcinol and formaldehyde, we have to be careful also not to catalytically decompose the molecule. And if you're interested, I'm happy to share these results and show that we're not decomposing the HMT during gelation. We think the pyrolysis step is a problem for decomposition. But we were able to recover these materials after synthesis. And one thing I wanted to share today is this really beautiful TM image that our collaborator Rhonda Stroud took at the Naval Research Lab. You can see these very sharp facets at the surface of the diamond that we make. If you zoom in and look at the high-res spectrum, these are 111 planes. We think this is most likely a 111 facet of the diamond, which is consistent with what you see in a detonation material or a milled sample. But we've done a lot of electron diffraction with these materials as well. We can see some graphitic domains. This inset shows the 002 peak of graphite. So there's some turbostriatic graphitic domains that are also forming in this experiment. But we can clearly index these peaks to cubic nanocrystalline diamond. One other really interesting observation that we've seen recently in the electron diffraction is just after the 311 peak for the nanodiamonds is a shoulder. And this could possibly be a graphitic peak in the sample, except we're not quite sure why its intensity is less than the 002 peak, which should have a higher intensity. We're interpreting this additional peak potentially as twinning planes and maybe even a hexagonal phase, possibly hexagonal Lonsdaleite, or at least AB stacking in the 111 direction, but possibly just a twinning plane in this material. But this is the EEL spectrum of the diamond. You can see this characteristic second gap in the electronic density of states. And then this is a EDAX map of nitrogen, argon, and also carbon in the diamond materials. You can see little points of argon emission, little point defects. In this sample, we've also seen some very enriched regions with argon. We think these are not solid FCC inclusions in the diamond. The signal just isn't intense enough to be a solid phase. We also don't see it in the electron diffraction. But we think that these could be little pockets of gaseous argon, possibly trapped between grain boundaries, but between individual grains, it's hard to say. But this is work that Abby has done a great job putting together, and we're just getting ready to submit. It's in submission as we speak. The other thing I wanted to share is some recent optical properties of these nitrogen-doped diamonds. This is the hexamethylene tetramine-doped diamond. We've been able to see, I forgot to mention, there's a 5-fold increase of nitrogen in the carbon materials we make with HMT as opposed to without. We can see this in terms of X-ray EDAX spectral intensities, and we've also done some elemental analysis to show there's about 5 times as much nitrogen in the molecularly doped samples as compared to the undoped samples. We've also seen a 5-fold increase in the photoluminescence of these diamonds. So they're much brighter than, they have much more emission than the undoped control samples. This is a high pressure spectrum showing the negatively charged NV center shifting to high pressures. This is at about 27 GPa, but we're still unable to answer the question, have we made B centers? This is one question that we're trying to answer. Unfortunately, it's really hard for us to do ultraviolet visible emission or absorption spectra on this small sample volumes. We just don't have the capabilities to do that currently, and we haven't been able to see this in infrared absorption convincingly yet. We haven't been able to do IR transmission as well. But what we have done is we've made some ab initio quantum cluster calculations of the vibrational density of states of the B center. And there's some clear differences, particularly at lower phonon frequencies, around 1100 wave numbers. There's some spikes in the EDOS. This is an H4 aggregate, which is slightly different than the B aggregate, this N4V complex. But one thing we'd like to do is use low loss EELs to do vibrational spectroscopy, aloof EELs measurements. And we might be able to see this vibrational signature of the B center using low loss EELs spectra. And these calculations will help guide those measurements. But I'd like to finish today with a quick overview of some very recent work that we just posted to the archive last August. And I mentioned this, I started sharing some of our preliminary efforts way back in 2018 at the MRS Nanodiamond Symposium. I wanted to give a quick update. And the motivation for this, this effort is in a lot of diamond materials, no matter how you grow them, they will have defects either in the bulk of the material or on the surface of the material. It's very challenging to get nanodiamonds that are perfectly homogeneous without, for instance, carboxylic acid groups or hydroxyls or other hydrogen passivation or graphitic domains. So this is a TM spec image of a diamond that we've been working with from Atomus, and these are really fantastic materials for doing ODMR spectroscopy. They have very bright NV centers, and we've been using these for ODMR measurements. But they're on the order of 100 nanometers, sort of milled from bulk HPHT materials. We did some EPR measurements on these samples. They have around 40 ppm substitutional nitrogen. So these are fitted, very faint P1 center peaks. And then there are also some paramagnetic surface states just from the milling and processing that we use. We think there may be also some A-center aggregates. This could possibly be an A-center, sort of a nitrogen cluster in these materials. We're not quite sure. This could also just be strain and some contrast effects in the bright field image. But this is an EPR spectrum showing conclusively proving that there are P1 centers in these materials. Then we've made some very nice, more recent infrared absorption measurements. So I want to give thanks to Stefan Stoll at UW for helping us with the EPR measurements, and also Ken Kuno at Notre Dame. This is photothermal heterodyne imaging spectroscopy, where effectively you're using nonlinear difference frequency generation to produce very high spatial precision, very localized difference frequency photons in the infrared region. You have a secondary probe laser that probes the thermal deflection of that local sample after absorption of this infrared range. And we can see what we could potentially identify as B centers in these HPHT materials. This vibration region has been correlated with A centers, sort of nitrogen aggregates. We see some enhanced absorption in the diamonds that could be indexed to carboxylic acid groups or hydroxyls potentially. There are also some other carbonyl or water absorption. We have carbonyl and water absorption bands. So the main thing I want to share is diamonds will always have some kind of background absorption that can limit their applications in quantum sensing, for instance, like ODMR. So one approach we've been working with recently is trying to use solid state laser cooling to compensate for that laser heating induced from, say, a 532 nanometer pump laser. So if you've not seen solid state laser cooling before, I wanted to give a quick introduction. This concept was first proposed way back in the 20s for sodium metal vapor gases. The idea is you can have an atomic or ionic transition with a low energy, and then some kind of thermal collision or phonon upconversion mechanism can upconvert the electronic excited state and cause it to emit a photon that's blue shifted from the wavelength that was absorbed. So if this is efficient enough, if you can get near unit, 100% quantum efficiencies, you can pump a material on with a red laser, say, and a red line, low energy, the low energy side of its absorption band, and then it can emit a blue shifted photon that carries away both the pump energy you pumped it with and whatever thermal excitation, whether that's a collision or phonon from the material. And it cools, in general, a bulk material. My colleague, Mansour Sheikh Bahai at New Mexico has published, this is a really great review article I wanted to point you to in case you're curious about the material. Their group is a world leader in terms of reaching the lowest possible temperatures. They've recently published a paper showing you could cool the ceramic yttrium lithium fluoride doped with ytterbium ions to about 90 degrees Kelvin from room temperature. So this is, getting close to where you could liquefy nitrogen. And typically for ytterbium, they pump at about, in the near infrared, about 1020 nanometers. The emission band is very broad, but it emits approximately 1000 nanometers. Just to give a little more physical insight into what's happening here, the ytterbium 3+ ion is substitutionally doped in the ceramic crystal. This is an F13 system, and spin orbit coupling offsets a doublet F7 halves ground state level from a doublet F5 halves manifold. And then crystal field splitting can modify the f orbitals of the ytterbium ion a bit further, depending on the point group symmetry of the ceramic. So if you have high symmetry, octahedral or tetrahedral point groups, you get a triple level, which has a degenerate middle state below a double energy scheme with a degenerate lower state. But in this ceramic, we have a lower symmetry S sub 4 point group. So all of the f orbitals become non-degenerate. You have 4 levels under 3. So what we're doing is pumping at 1020. The other physical thing I wanted to share for those of you who have worked with lanthanides before is we have a F13 system, which is missing one F electron. So I think of this kind of like, half-filled orbital at its ground state, and then thermal energy will at room temperature will excite this hole to the base of the doublet F5 halves level. And the photon pumps this. You could think of it kind of like the hole equivalent. You can think of it like an electron getting pumped up to the doublet F5 halves level. The hole gets sent to the lower level, and it's optical phonons that upconvert this hole to higher energies. This is what's kind of giving the thermal energy from the crystal. And then an electron can relax from this upper manifold, the doublet F5 halves configuration, down to this lower doublet F7 halves level, changing the configuration. And that's what causes the blue shift, just to explain it in a little bit more depth. So what we've done more recently is we've taken these ceramics. These are yttrium lithium fluoride ceramics doped with ytterbium, and we've coated them with atomous nanodiamonds. These are milled HPHT atomous diamonds that we've color-coded red. I don't know how well it comes through in the slide, but these are very bright, very nice materials that we can get ODMR signals from, and NV emission, very bright NV emission. So this ceramic is supported on a cantilever on a silicon wafer. We pump these diamonds in vacuum with a 1020 laser beam. This is how we pump the cooling. Then we have a secondary laser that we can pump to excite the NV center to do optically detected magnetic resonance. And so we're looking at this zero field splitting parameter, this D parameter. And I want to give a shout out of thanks to Nick Vemivakis at U Rochester, his group, and also Fedor Yelezko's lab at U Ulm, who have really helped us tremendously to understand and develop these ODMR measurements. And so if you look at the zero field D-splitting parameter, it's very temperature sensitive. It typically shifts on the order of 70 kilohertz or so per degree Celsius. So we can monitor this shift of the zero field splitting parameter. And as this blue shifts, as it moves to higher energies, this is correlated with decreasing the temperature of the diamonds. So we've been looking at this parameter and using this quantum sensing approach to quantify the temperature change of the diamonds on the ceramic crystal. And once we saturate the absorption of the ytterbium, the cooling stops. But we can control the temperature we can effectively compensate for any intrinsic heating of the diamonds, bringing it back to a 0 Kelvin heating situation, and even cool the materials to on the order of 10 degrees Kelvin below room temperature. And these measurements were in air. So, we can do these samples. And if you want to get a higher brightness, higher intensity for ODMR spectra without photo bleaching or darkening your diamonds, or photothermally damaging them, shifting the zero-phonon line of the NV center, this is a way to optically and rapidly compensate for that heating. So I just wanted to share this, our latest and most exciting results at the end of the talk. So with that, I'd like to say thanks again to Olga and Eugene for all of your efforts to organize these seminars. They've been really great. I wanted to say thanks to the audience for coming today. And I also wanted to mention, if you know of anybody looking for a postdoc, or if you happen to, if you're a student or postdoc interested in this direction, I'd be delighted to talk more about openings in our group. But with that, I'd love to take any questions, and thanks for listening.